Hey guys, welcome back to my YouTube channel. Alright, online people, can you see the camera? We are looking at the live chat, so for anyone online, we are looking at the live chat. You're welcome to put any questions in there and we will try to answer them once we see them. If anyone's online. People in person, can you see the camera clearly? Awesome. Welcome to ELEC2141 crash course, Digital Circuit Design. This is my book from last year when I did the course. Today in this crash course, the first about half an hour to 45 minutes we'll spend just going through revising a little bit of key theory. We're not going to revise what an AND gate is because you shouldn't be here if you don't know what that is. But we will go through some basic principles like gate input cost and flip-flops, latches, muxes, decoders, etc., etc. After that, we'll go through some past paper questions that I've collated. I've picked 4 questions that I think kind of well represents basically the entirety of what you're going to come across. These questions we're going to have a break probably after the content session. So I'll upload these questions onto the forum in that time, and you can download from there if you want to have a copy while we work through it. The questions, one of them is from 2009. It's a really nice question. The other of them are more recent times. The content mostly hasn't changed. That being said, question?
Who are you?
Who am I? Sorry, my name is Sudarshan. That's Otto. Is that okay?
Yeah.
Okay. We're going to jump right in. Might need to turn this a bit. Wait, I'll start writing. Tell me if the angle feels a bit awkward. But basically, we have, this is digital circuit design. Digital circuits can have 2 values, a 0 and a 1. Therefore, mathematically, we can represent this in binary or base 2, where any value can have a 0 or a 1. In circuits, we are familiar with standard resistors and like a battery, etc., right? So similarly, we can do something in digital circuits called logic gates. What these do is that these take in 2 inputs, do some magic here, and give an output. You can have AND gates. This is an AND gate. It tells you if both the values, let's call this A, B, if both the values A and B are true, then the output is 1. We also have an OR gate, which can take inputs. We have a NOT gate. We have an XOR gate. And then we have a NAND gate. This is a NOT AND. You will notice that the symbol for the AND and the NAND. Sorry. Please tell me if the page goes off the screen, yeah? Because I can't see up there. The symbol for the AND the NAND differ only by this bubble. And a bubble after any type of symbol means the inverse of the previous. Just like this one, this has a triangle and then a bubble after it. So this means it takes in the input and it gives out the inverse of that input denoted by the bar on the top. If we did not have the dot and just a triangle, this is called a buffer. This literally takes in the input and copies it to the output. This may seem stupid, but this does have applications in circuits, because if you think when 2 circuits are connected to each other, in like a practical circuit, they can influence each other based on resistances and voltages. Whereas what this does is this copies the input and sends it in the output so that it's almost always constant. These are probably all the gates that you'll come across. A thing to note is that this is an XOR gate. It can only have 2 inputs. I have drawn these gates here, all with 2 inputs. These gates can actually take more than 2 inputs. You can take the AND of multiple values. You can take the OR of multiple values. However, you can only take the XOR of 2 values only. The XOR is denoted by the plus with the circle symbol. I hope that's prior knowledge. And now you'll see that you can have several inputs to a gate, right? So a very standard thing that you want to calculate is how many inputs there altogether. Because the more inputs you have, the more kind of costly it becomes. So we denote this by gate input cost, or shortened for GIC. And the gate input cost, if I have a function, let's say f equals AB plus C naught D plus E plus C naught. There we go. This is a big function. I hopefully you understand what it means. If I take this and I want to calculate the gate input cost, this basically says if I was to draw it out using these specific gates, how many inputs would I have into all these gates all up? The gate input cost, there are two ways of calculating it. It can be algebraic or not algebraically, kind of mathematically or graphically. We can do the graphical one first. The way we can do that is, so this is an A and B, so we can take A, B, and them together, and we have an output. And then this one takes a C naught, so we can take a C, pass it through a NOT gate, take the output, and then we have a C naught D plus E. D plus means OR, so we can take a D E, take that through the OR gate, D or E, and then we're ANDing the C and that, so we can take a copy, take that, send it through an AND gate, and therefore this is AB, this is C naught, this is C naught D plus E, and then we have to OR all these together, so we can take that into a nice big OR gate, and this is our output F. To calculate the gate input cost, we literally count how many inputs there are to our gates. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Therefore, our gate input cost is 10. The alternative way is using the literals, terms, and complements method. What this means is that through your formula, you count the number of literals. A literal is any variable in your function. So here we have 1, 2, 3, 4, 5, 6. We have 6 literals. And then you count the number of terms. A term is a collection of variables together. So we have one collection here, we have one collection here, and then this itself is one collection, right? We have 3 collections. You could argue we have one big collection, but we don't use that because if you look at the output F, that doesn't actually become the input of anything else. So therefore, we take all the terms inside here. We have 1, 2 here, and then the one big one here. That's 3 terms. And then in our function, we count how many unique complements do we have. We see that, well, if I redraw the function, AB plus C naught D plus E plus C naught, you'll see here that we have 2 complements here, C naught and C naught. However, they're the exact same, they're not unique, therefore we only have one unique complement. So that's one unique complement. Add those up, you get 10, which is exactly what we calculated when we drew it out. Does that make sense? This is gate input cost question.
Do you mean 5 literals?
1, 2, 3, 4, 5, 6. No, the function continues to the very end here. 1, 2, 3, 4, 5, 6. Cool? Question?
So it's the repeat of the C, yeah?
Sorry?
The C repeats.
Yes. So when we count literals, we count every single term in the thing. If this was actually A plus all of that, we would count all these individuals as literals. Only when we look at the complements do we take the unique ones. Question?
Is there a reason why it's 3 terms and not 4 terms? Because you've got the 3 plus sign and then the 1 and between the C and the D.
Let me rewrite this.
No, I was confused.
All good?
No, it's 2 plus symbols and 1 and gate. Yeah?
Yeah?
Yeah, okay, cool.
Awesome. And you can check that if you have that much time to burn, you can always just draw out the function and check that both methods yield the exact same value, which is a good sanity check. Is it displaying? Yeah, okay, all good. Okay, so we've found two ways of calculating the gate input cost. There is something to note though, is that we can simplify this function. If you remember your Boolean algebra simplification tools, you'll know that AB plus B, well, let me write that, AB plus A, just for easiness here. If I have AB plus A, that's equal to just A. The reason this happens is if you think about it conceptually, this function is true when A is true, right? This section is true when A is true. This section is true when A and B are true. The final output is true when either of these are true. This will be true more times than this will be true. If this is true, that means A is already true. So this is redundant. This is called the absorption theorem. Therefore, we can actually simplify this big mess into just AB plus C naught, and we get the exact same output. Fun piece of trivia. Next, we have something called Minterms and Maxterms. We want a way to generically and standardizedly refer to functions and their implementations, right? So we have something called Minterms and Maxterms. You'll notice that if let me just draw up a good old truth table. Am I on the screen? Yep. 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1. I hope you're familiar with this way of drawing up truth tables. You alternate this one, and then alternate this one every second time, and alternate this one every fourth time. If we take this, I call these A, B, and C, and I just add an extra I column here, just for like the number, or like, let's call it N. This represents a 0, 1, 2, 3, 4, 5, 6, 7. There you go. So a minterm is a way to represent this combination algebraically. So this is true when is true. Does that make sense? If A was 0 and B was 0 and C was 0, then this output is true because the complement is 1, 1, and 1. This is called your minterm, or your sum of products when you add these together. This is called a SOP method. The minterms are ANDed together, and a 0 is represented by a complement, and a 1 is represented by the actual thing itself. These are the corresponding minterms, and a max term is the alternative way of doing this, which is sorry, one second. A or B or C. This is your max term. You'll notice that if all of these are 0, the output is 0. So this is your max term. It's summed together. So when you have several max terms, this would be the product of sums method. Minterms and max terms, we can represent the max term, maximum is big, and the 0th max term would be capital M of 0, or the 5th max term would be capital M of 5. The 3rd minterm would be lowercase m of 3, and just as a quick refresher, the M3 would be represented as A naught B C. Does that check out? Awesome. Those are your minterms and max terms. Therefore, if you were given a truth table and an arbitrary function output and asked to find the equation, what you could do, yet another truth table. 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Let me draw the n column just for fun. The n column is strictly not necessary, but I find it really helps me when counting these, so I don't have to actually figure out what each number represents later on. And then if I have my f, let's say 1, 0, 1, 0, 1, 0, 1, 1. This is our arbitrary function. To represent this function as a sum of minterms or a sum of products, what we do is we notice that f, that's an E, f is the sum of minterms 0, 2, 4, 6, and 7. So we can write that as the sum of minterms 0, 2, 4, 6, 7. And when we expand that out, we get minterm 0 is A naught, B naught, C naught. And then minterm 2 is A naught, B, C naught. And then 4 is B naught, C naught, plus A, B, C naught, plus A, B, C. Cool. Therefore, if we were given this truth table and asked to find a function that represents it, this would be our answer. This is a very common, very first question, very free marks, so make sure you can do it. And you can alternatively write it as a sum of max terms. When you're doing max terms, they can also specify in the question to represent it in which particular form. So you can also say f is the product, that's a pi, p for product, of max terms, everything with a 0. So that is 1, 3, and 5. I will not write that down because I cannot be bothered. Now note that the results we got are very long. And I'm sure there is some instinct in you that says that we should be able to represent this innocent-looking function less awfully than that. And if you just lightly observe here, there are ways that we can easily simplify this. If we factor out the a here, we get a b naught c naught or b naught c, and then we can factor out that b c naught. We can do a whole bunch of factoring. That's a pain in the back. Introducing K-maps. A K-map is a standardized way to represent a function and generate a simplified expression for the sum of products method or the product of sums method. It is not the absolute simplified expression. It is a simplified expression in the standard form. Excuse me. The way we draw a K-map is, let me draw a nice big grid here, put a line through it. We'll notice that we have 8 possible values this can take. So we want a K-map should have 8 squares. There we go. And we assign each square a value corresponding to the function value, right? So if we say, let this be the A axis, let this be the B and C axis, we note this 0 and 1. A funny thing about K-maps, we see 0, 1 here. You would think it just keeps going sequentially. It doesn't. This is a very common mistake when marking. Make sure that you go 0, 0, then 0, 1, and then 1, 1, and then 1, 0. Think of this as a gray code. Only one variable changes consecutively at a time. You should never go from 0, 1 to 1, 0 because then you're flipping both bits. Bad. This way, we can say that this square, ABC, has a value of 0, 0, 0. This represents the 0th value. 0, 0, 1 is the first value. 0, 1, 1 is the third value, etc., etc. So we go 0, 1, 2, 3, 4, 5, 6, and 7. I always like to number my K-maps like this. You don't have to. It makes it really easy when you're trying to copy over from your truth table. And then we say that the outputs of our function here is 0 for 1, 3, and 5. So we place a 0 in 1, 3, and 5. And then it is 1 for the rest of them. And 1. With a K-map, our aim is to draw the biggest... It's not always the biggest square. It's the biggest standard shape with an area of a power of 2. That's a complicated way of just saying it should either be a rectangle or a square that has an area of 1, 2, 4, or 8, right? So we can draw a rectangle of area 2 here, We can't draw a rectangle of area 4 here because it's 0 here. We want to join up all the 1s. So we have 1 here. Let me bring an eraser. Apologies. So you want to draw the biggest rectangles or squares. We can draw 1 here, and 1 here. With a K-map, you need to think in like the 4th dimension. It's a Mobius strip. The K-map wraps around in every single axis. So what you can have instead,
It's like Pac-Man.
it really is. It just infinitely goes on and on. And then 5 variable K-maps are not covered in this course, but they're absolutely cursed, and they wrap around in so many dimensions it does not make sense. Anyways, if we take this and we wrap it around, we'll notice that we can make a nice square like this, connecting these 4 ones, and they are joined on the kind of wrapped axis, right? So there's one big square there, and then the biggest, we have this last variable left we want to like include. The biggest shape we can make is unfortunately only this rectangle. Excuse me. So now we have 2 final shapes on here. We have the one big square around the edges, and then this rectangle here. I don't know which way is taught in the lectures of how to identify these. I have seen several ways before. The way I like to do it, it might not be the easiest one, is I like to see which of the values do not change between the squares. This big square here on the outside, on the a-axis, the value changes, so we ignore the a. On the BC axis, it's 0, 0, and 1, 0. So the b value changes, so we ignore the b. So this last square is represented by a c equals 0 or a c naught. And then this square over here, the a does not change, so there is an a, and then between b and c, the b does not change, so there's a b, and then the c changes, so the c gets ignored. So this final truth table, the very same one we drew up here, did I? No, I didn't. Oh, this one here, yeah. This same one, which we represented as this big sum of products, is actually equivalent to just AB plus C. Okay? This is a K-map simplification method. You should be well familiar with this. Just for a bit of refresher. Note that in a K-map, you can also have something called a don't care condition. If you do not care what the output of that function is at that point and at that set of inputs, then you have an X or a don't care. This comes up when you know that an input should never be possible. If this function, say, represented, I had 5 friends of mine, and each friend had a different ID. I know that IDs 6 and 7 are never going to happen because I only have 5 friends, right? So that way I can put an X in this column and say that I guarantee you it'll never happen, so I don't care what the output is. So in a K-map, an X, if, just for argument's sake, we had an X here, we had a big X here, an X serves as a kind of wildcard. If it helps to make our squares bigger, then we incorporate it in our squares. If it doesn't help to make it bigger, then we leave it be. So if an X was here, then we can make one big nice square here. So we do include it, right? However, if the X was here instead, this X does not aid us in making a bigger square. Because this is 0. So I have this square here. And using this does not help me at all. So in that case, I would ignore it. So an X is a kind of Uno wildcard, if you may. Cool. Using these are very, very basic gates, and it kind of may seem useless. To get more into it, there is something you can make called a decoder. A decoder, like I said, I have 5 friends of mine. Let's make it 4 just so that it's easy and it's power of 2. I have 4 friends. Let's say 0, 1, 2, 3. And this is A, this is B, and 0, 1, 0, 1, 0, 0, 1, 1. Each friend has a separate ID. Using these IDs, I want to give each of them a different alarm sound. Let's say if they ring on my door, they have an ID, each person has a different sound. Using that, you want a nice way to be able to trigger, let's say, my alarm bell, right? So you want a way to kind of give each of these a very unique line of its own. Therefore, if it was 0, 0, and then I want light bulb, I don't know, W, X, Y, and Z, right? So kind of vaguely, if I drew a random box that has some magic functionality, which takes in my A and B, and then I have my outputs W, X, Y, and Z, I want different sets of A, B to control different individual lights. Yes? The way we do that is called a decoder. A decoder takes in a combination of values that represent a binary number. This represents 0, 1, 2, 3, etc. And it outputs, let's call it W, X, Y, and Z. It outputs a unique value for each of them. So this would be like that. Right? This is functionally what we want from our little friend notifying system. We want, with these inputs, if ID number 1, then turn this light on. If it's ID number 2, then turn this light on, etc., etc. This is called a decoder. And just to reiterate, a decoder takes in a combination of numbers that represent a binary number, and it turns on only ever one. It turns on the one single output that corresponds to that value. So in a decoder, we would actually represent this as, instead of W, X, Y, and Z, we'll have X0, X1, X2, and X3, and an input 0 would turn on the X0 line. Input 2 would turn on the X2 line. Make sense? Awesome. And then another common tool that we use is called a multiplexer. On this TV screen here, it's currently projecting from this document camera. On this control panel, I can select a different line to come in. I can make the computer be projected, or I can make my laptop be projected, or I can make it stream from Echo 360. This uses a multiplexer. This takes in a large number of inputs that are always feeding in at the same time. This computer's on, my laptop's also on. So all the inputs are going into this system, but it's taking them and it's saying, no, I'm only going to pass a single output through. It's only going to pass this little document camera through, using something called a select line. So I have several of my inputs, and I want to select which one I'm going to output, right? So if I draw this as a kind of truth table, let's say I have inputs A, B, C. Well, that's not a truth table. I have inputs A, B, C, and D. Using my magic black box here, I have two control lines or two select lines. Let's call this C1 and C2. And then if I had C1, C2, output 0, 0, 0, 1, 1, 1, 1, 0, 1, 1. Classic truth table. If it's 0, 0, represents kind of the 0th input, so the output should be A, B, C, D, etc. Right? This is called a multiplexer. Again, what it does is it takes in a control. Using the number that that control represents, it passes through 2, 3. It passes through that numbered input. Any questions? Awesome. This all should be prior knowledge. Otto is now going to go over arithmetic in binary. This is not always fun, but it will be in your exam. Would like your
It will be fun in your exam, more like. All
Sorry.
right. So let's do this. So fundamentally, I'm going to cover today a bit. Hope that's the least bit legible. Two's complement.
Oh my god.
One's complement. Meaning of overflow. Addition, subtraction, unsigned versus signed, and status flags. So let's get on with this. All right. So, where to start? Starting with two's complement. Okay, so two's complement. What does it mean? Really, the way that I like to think of two's complement is what do I need to completely screw over the binary numbers that I have. So if we begin with the binary number, let's just start with this one. This is the binary number for 8 plus 3, 11. So this is 11 right here. If I wanted to find 2's complement, and I'm only restricted to 4 bits, then what I really need to do is see what I need to add in order to get this number, which would be 16, right? So I'm really finding my complement to find the next power of 2, okay? So this is how I like to think of 2's complement, and there's a very, very nice way to do it. If we were to just go ahead and cheese it, we go ahead and we know that, okay, you add 5 to 11, you get 16. Fantastic. What's new? Well, if you have a massive number, this is going to be pretty difficult to determine just by straight up doing it. So we propose 1's complement, okay? Now, 1's complement, really all it says is I'm going to go ahead and say, I need to make this number, okay? I need to make all 1's. If I want to make all 1's by using some addition to my given number, what do I need to do? I need to go ahead and fill in the 1's that were previously zeros, the zeros become 1's. Okay, 1's become zeros, zeros become 1's. So if I go ahead and I complement this, this turns into 0, 1, 0, 0. And the way that we see this is we have A XOR B is equal to 2 to the power of n plus 1 minus 1. Okay? This is just a little bit of logic behind how we come up with and how we use our 1's and 2's complements. Okay? It's somewhat straightforward when we start understanding that, okay, we really just want to see how we can lose all our information in the lowest number possible, really. So, if we go ahead and configure this, we understand that if we do A XOR B plus 1, that's going to give us 2 to the n plus 1, and this circles back up here to give us a 1 out the front. All right? And so, when we use this kind of idea to figure out how XORs work, we want to say, okay, B equals 2's complement of A. So, first I do A XOR with 2 to the n plus 1 minus 1. So really this is just going to be our series of 1's. If I XOR with that, I end up with my 1's complement. So this is 1's complement, because I've really just flipped over every single bit I have there. And then I'm just going to add a 1. Okay? By adding the 1 on the end, I make 2's complement. Alright, so that's just the general gist of things. We know how XOR works. This little subtraction is a little goofy, but we understand it's just filling it with 1's. And then we add 1 at the very end to get something that's going to sum back to 2 to the n plus 1. Okay, so that's just how the arithmetic there works. And so let's give a little example. Very typically, the finals questions are going to be concerning like long strings of bits, maybe convert them from hexadecimal to binary, and then do a little big 2's complement on it. Okay, so let's just do a little example over here. I'm going to think of a couple random letters. Let's go with A, D, 1, F. Here's my number. Here's the number. It is in hexadecimal. I can tell that from the 0x at the front. And so we can convert this to binary. The way that I like to think of binary numbers is, hexadecimal numbers. We go 0 to 9, and then from there you go A to F. And so A, 10 through to 15. Okay? So A is going to be 10. How do I express 10? I express it as 8 plus 2. So A, I also like to divvy these up into each of their segments so I don't lose anything. D is going to be the fourth letter, so 4 plus 9, 13. We go 8. Now we need to add a 5, which is 1, 0, 1. And then 1 is just 1. And then F. F is very special because it is our last value. We know it is the greatest. Okay? So I've segmented this little number over here. Now I'm going to find the 2's complement of it. So how do we do that? First we find the 1's complement. So I go ahead, I XOR every single bit.
XOR is a fancy way of saying is invert the bits.
Yeah. There we have that. That's a long trail of zeros. And then I need to find 2's complement by just adding 1 bit. Okay? And that's very simple in this case because there's just zeros at the end. Okay? And I copy the rest from here. All right. So, trying to stick within my same divisions, it just helps me segment it out, and it can help us make sure that our working out doesn't become a mess. So, any questions concerning 1's and 2's complement? We all cool with that? Very strong in that aspect? Let's hope. Okay, let's move forwards. Just recalling back on what we were going to do. What does overflow mean? I mentioned...
Back to the previous page for a hot second.
Yep.
Just one comment. The actual...
Oh, sorry. Yes.
Bring it up. So the 1's complement is flip all the bits. The 2's complement is add 1 to that. That's a long set of steps. If you want the easy way, or the shorter way, it is keep all the bits until the first one that you encounter, and then flip the rest. Cool?
So to reiterate what Sudarshan mentioned, what we want to do is we want to find the first one in the sequence, right? When we find the first one, we can keep that as a 1, and then we can flip everything else. So in this instance, we've flipped everything after the very first one. If I were to find the 2's complement of, per se, let's try 1, 0, 1, and then tons of zeros, what I would do here is I would find my first one looking in from the right-hand side. I keep that 1 there, and then I flip everything else. So I get 0, 1, 1, and then string of zeros. And to double check all of these in any case, we can just add these together. And what you should always get is, okay, these two add to a 0, carry the 1, and you continue carrying until it is pushed outside of your limit, okay? And we get a little overflow kind of bit. So, thank you very much, Sudarshan.
That leads nicely into the next topic.
It does. It's like it was planned. Now, let's talk about overflow. So, overflow is very much the idea of, okay, what happens if I push too far? Now, essentially, in computers, we have a restricted number of bits to assign our number to. And now that's always going to be a challenge in how we deal with that, so we come up with a little thing called overflow. Overflow really just means that if I list out my numbers, let's say I'm listing out 2-bit numbers, okay? I got my first number, which is 0, 0, 1, 1, 0, 1, 1. So 1, 2, 3. If I push any further, the computer goes back to 0, 0. So it's a 4 question mark. And it's because we've got to carry out the end, which has been chopped off, right? And so here we would say there is some manner of overflow. It is a pushed forwards manner of bit, because we've pushed too far in our summing. Now, mind you, this concept of overflow does change a little bit when we start talking about addition and subtraction. It is very, very much tied to what it means to add things, what we're expecting when we subtract things. And that'll lead a bit nicely into slightly future topics, but let's just talk about addition and subtraction for the time being. Addition is going to be rather straightforward. We kind of did that 6 times right over here, but it's just addition in your base 2. Okay? So base 2 really just means we have 2 numbers, those are 0 and 1. We're going to add them together the same way we would regular numbers in decimal. So in the same way that I might go 1, 2, 3 times 5, 7, 9, just in decimal. Let's hope that I'm able to do this. We carry a 1, get 7. Okay? So really, we're just doing this same thing in binary. So we're restricted in the number of symbols we can use, sure, but that's really all there is to it. So if I add these two 5-bit numbers together, 5 bits is very funny because nothing really uses that. I can carry the 1, carry forwards, and then, oh, we get a final carry, which we would call, in this instance, a manner of overflow. Mind you, so far we've been talking about unsigned numbers, okay? Which is somewhat important for this discussion, but realistically, if you have anything that pushes this carry forwards, but there's no carry over here, that is going to be what we officially call an overflow in terms of addition and subtraction, which we'll see a bit later with status flags, okay? So, I mean, I feel like we got addition out of the way. We feeling strong with addition? Fantastic. All right. Now, as always, subtraction comes after addition. Now, there's this very, very fantastic idea of pushing out a digit. Now, when we talk about binary numbers, addition comes very nicely. Subtraction, though, a bit more difficult. So what we do is we understand that, okay, if I do a plus a complement, what am I going to get? Mind you, this is going to be a 2's complement that I put over here. I'm going to denote it like that. It's probably not officially denoted like that. They usually use words, but I'm going to call it that because I'm a bit lazy. So if I do a plus 2, the 2's complement of a, I should arrive at 2 to the n plus 1, right? Where I have this 1 existing out the front, and then the rest are trailing zeros, as we've seen previously. So, to understand what subtraction really is, I say that this thing is going to be 0. Now, why is that? Because realistically, when I look at the computer, I see, oh, a number's fallen out. All I can see are the zeros over here, and therefore, it's 0 for all intents and purposes. And we're going to call it 0 because that's all I can see. So I'll actually just like draw a little arrow there because I don't want to get in trouble. And so we can see that by taking a complement, 2's complement more specifically, this is going to be equivalent to minus a. Now, mind you, this comes with a little caveat that I'm going to be talking about particularly for signed integers. So signed integers, this is very much going to talk about how, okay, if I have a 1 at the very front, I'm going to call that a negative, okay? If I have a 0 at the front, that's going to be a positive. That's how signed and unsigned work. So signed, the very first bit is your sign bit. For unsigned, that's just a big number, okay? It's your biggest bit, most significant bit that you have. Now, this isn't really the most important when we start talking about negatives and such, but it helps us try and figure out the order of things. So if I have a number given by 1 and then followed by a ton of zeros, this isn't just going to be negative 0. Okay? We should understand that, okay, if we consider the 2's complement form of logic, this instead is actually going to be the 2's complement of pretty much itself. Now, why do I say that? Because following 2's complement, I find my first one, and I keep that, and I flip everything to the left of that. There's nothing left of that. So you'll actually find in signed integers, signed binary numbers, you'll end up with lists that go from, let's say we go 0 to 7, just by going 000 to 111. Mind you, this is all with a 0 at the front. However, going backwards, we can get a -8. Now, why is this? Because we're using 4 bits. 4 bits means we can use 16 numbers. 16 numbers means 8 through to 7, inclusive. The inclusive adds that little 1 at the front. And so we have 8 over here, which is pretty goofy, because 8 and -8 would be represented by the same kind of numbers, which gets a little messy, so we don't really like doing this. Moving forwards, subtraction. So, typically when I do subtraction, I'm going to be adding the 2's complement of my other number. So if I need to do a minus b, this is just going to be a plus 2's complement of that. And then potentially, I'll say maybe minus 2 to the n plus 1, okay? Which is where we disregard that overflow number. All right, so let's give a little example of subtraction, because that's typically where logically a lot of people goof. So let's go ahead and think about this. I'm going to make a random binary number. Add another. And we're going to try and subtract another number. Let's try and subtract this manner of monstrosity. Now, I'm just going to divide that into segments so I can keep track of it very nicely. If I want to subtract it, I have to take 2's complement. So this is going to be equivalent to, I keep my same top number because that's staying the same. However, I need to add the 2's complement. I find the first one, I keep everything right of that and itself, and then I flip everything else. So I get a 1, 0, 0, 1, 0, 1. Okay? Now I'm going to add these together, and let's see what we get. 0, 0, carry the 1, 1, carry the 1, 0, carry the 1, and then 0, carry the 1, 1, 0, carry the 1 outside. And we end up with this out here. Now, I think this segues pretty well into just like what overflows and what status flags we would use here. But we'll get back to that in just a sec, and just think about what just happened. If I were to subtract these two numbers, I know that, okay, sure, let's consider unsigned, just because that gets a little less messy. I know that this is the biggest number, it's on the top, fantastic. And I'm subtracting a smaller number. Why can I tell this? Because it's got a better, most significant bit. If I go ahead and I subtract the smaller number, I'm going to get some manner of positive number. I can double check my answer by adding this result to, adding what I subtracted to this result to get my initial value. And so, to double check, 1, fantastic, 1, fantastic, 0, fantastic, 1, and it moves forwards, and it's fantastic. Okay, so we've double checked, that works. Now, we've got this nasty little 1 at the front. Now, a result of using 2's complement to subtract is that the way it works is flipping back to our little expression over here. On occasion, we'll have to remove this number, the 2 to the n plus 1. Now, the only instances where we wouldn't really need to remove it would be if we're actually staying negative. Now, when might that occur? That might occur, let's make a funny value. Another problem using very similar numbers, but instead we're going to be subtracting something much greater. Okay, so if I subtract these two, I take 2's complement again, a little bonus practice for us. 1, 0, 1, 0, 1, 1, 0. Sorry about that, thank you. All right, 2's complement, keep everything on the right of the first one, and then flip. And I end up with, funnily enough,
That's should be flipped.
which ones?
Should you flip this one?
So I'm just converting from here to...
Trying to. Oh, okay.
Yeah. And so, what we end up with is 0, 1, 1, 1, 0, 1, 1, 1. There's no overflow over here. There's been no push over. Now, what does this mean? This plays very much into our negative numbers and how we deal with signed values. Now, over here, I've considered them as unsigned, and I've added 2 numbers, and I very much know that it's going to overflow. Now, how can I tell it's going to overflow? Very simply, I've got 2 of my most significant bits, okay? And so, the way that we're going to define our status flags now, let's just recall we have let's just go in order of easy to determine. We got the 0 flag, that just means 0. We have the negative flag, which means negative. We have the carry flag, which is very much just talking about this carry over here, whether that's a 0 or a 1, at the end of our operation. And then we have the V, the overflow flag. Now, we understand that carry and overflow work on very different manners of conditions, okay? And so, we're going to go ahead and just explain more in depth what overflow means and how we determine it. In all instances, we will be determining overflow, the V flag, to be equal to Cn XOR Cn plus 1. Now, what do these mean? I'm just talking about the nth carry and the n plus 1th carry. So this is Cn plus 1, Cn, and we call our carry flag Cn plus 1. Okay? So this is how we define our flags. If it's 0, then I'm really just looking at a trailing line of zeros. If it is negative, mind you, negative is only useful for signed, I believe. Yes? Yep. And this is just checking your very first bit. Your very first bit. So I'll just do a little summary of signed over here when we get there. Negative just checks if the signed bit is active, and then carry if there is a carry, and then overflow only if we see both carries. So let's go ahead and give an example of overflow. We've actually made one just up here. Now, over here, let's just consider this addition. Now, considering this addition, we have the summation of two most significant bits, which gives us a carry out. Now, you'll note that this little rule is very much designed towards the condition of signed values. Okay? We can't go ahead and say, okay, this has to be not overflowed because whatever, but actually, sorry, let me take a step back there and double check my working. We see that there's no carry going into Cn, and there is a carry going into Cn plus 1, and so there should be overflow because we've pushed a bit out. For these instances, using unsigned values, your overflow is really, do we push something out? Because unsigned, we are really just talking about positive values. It's all positive, your most significant bit becomes just a really big number. And so if we push it forwards too much, we lose that biggest bit, the 2 to the n plus 1, and we lose information. And that's an overflow. Overflow is a characteristic of losing information or giving the wrong information. So there's that. Overflow, you typically go ahead and use for signed values. Now, let's go ahead and do a little summary on signed, and then we can get kicking with the practices. So, signed values, as we mentioned, it's this first value in a number. Okay? So this is how we're going to deal with signed. A 1 at the front implies it is negative. A 0 at the front is going to be a positive. Now, this plays very, very nicely into our idea of subtraction. Now, why is that? Because when I take 2's complement, I'm going to be flipping the sign. And that's very, very interesting. So let's go ahead and do an example of signed subtraction, because quite frankly, addition is somewhat boring. Let's talk about subtraction. So let's once again make up a random number. So let's do this. I'm going to use 10011, 5-bit number, of course. We see that it is negative because it has the 1 at the front. We could go ahead and be lazy and determine what negative number this is, if you ever want to double, triple check, and then just plug that into your calculator. But we're going to go ahead and subtract a another big negative number. Okay, so let's really just have some fun. So we do this, we note that these are two pretty substantial negative numbers. Why? Because remember, negative, to determine the magnitude of the number, you just take 2's complement. And so I see these zeros up the front, and that means I'm going to have to flip them into 1s, meaning I got 2 very significant bits in my positive magnitude of this number. I might explain that a little further in a little bit, but let's see how this goes. I subtract, so I take 2's complement of the denominator, I mean not denominator, just the subtractee. So I go 0, this 1 stays, everything else flips, and we're going to add these two together. And what we arrive at is 1, 0, carry the 1, 0, carry the 1, 0, carry the 1, 0, 1. That was rather perfect. So, let's think about this. We have this is a carry bit, so carry is going to be 1. Now, recall, we've done a negative number minus a negative number. Negative number minus a bigger negative number. Does it make sense for it to be positive? Yes, it does. And so, this sign bit, negative is going to be false, so we get a 0 bit there. I'm just running through the status flags as we do this. We double check if it is 0. No, it is in fact 1. So 0 for 0. And then our overflow bit. Now, over here we've seen that, okay, there was a carry on the last bit, and there was a carry coming out. So they're both 1, and therefore it is not overflow. Our operation has made sense, and we've used this funky little carry over here to push it out of being negative and being positive. Okay? It's a little thing to wrap your head about, but that's that. Very nice. So, does anyone have any questions for the gobbledygook I just sprayed? Strong with that? Okay, thank you. So, I believe that is going to conclude arithmetic. I'm going to hand you.
Speaking of cheating with the calculator, fun fact, if you have a calculator of FX 100 or better, you can do all the cheating on the calculator. Here's how you do it. Hit mode. You see here there's a base N option. Base N, so you want to hit that one. Hit number 4. And it's in decimal right now. That's lame. We want binary. You'll notice here there's a dec, hex, and wait. There you go. Dec, hex, and bin. You want binary, so you hit no. So we hit the binary option, and now it's in binary. Hit a whole bunch of zeros. The calculation that we just did here was 10101110 minus 01011010. We would like the output to be 01010100. The output, if we ignore all these zeros at the end, just the last 8, 0101 0100.
I was about to be fact checked.
Awesome. Cool. And that's how you cheat. Obviously, if a question is worth like 8 marks, this was one of the past paper questions that I had, prepared. So we can probably skip this later. But this is the 2019 past paper question, where it gives you 2 hex numbers, asks you to convert them into binary, and then calculate the binary addition and unsigned binary subtraction on them for 5 marks. Obviously, if you just write the answer, you're not going to get like most of those marks. So you would go through all the steps we just did, do the calculations, look at the XOR, calculate the V flags, do all these, write down the values of the status flags, and then to verify that you're right, then you can use this method. Cool.
Yes. So the calculator is very good at verification. And that'll be my part for content now. Handing back over to Sudarshan.
Now we really get into the kind of interesting part of the entire course. All of the beforehand was quite lame and it's just basic. The really new content is called Latches and Flip-flops. We want to build circuits that can actually do cool things. And in order to do a cool thing, you need to be able to actually have memory, right? You as a human, you have a memory. It might be bad, but you can remember things. Just like that, we want our circuit to have some memory. If we look at our previous circuits, a whole bunch of AND gates and OR gates, this can't actually remember anything. The output is determinant on the inputs, and it cannot be if there are no inputs, right? We want a way for the circuit to have some memory and do some cool things or do things in sequence, introducing sequential circuits. We have two types of sequential building blocks that we use. They are called a latch and a flip-flop. You should be more than familiar with this from your assignment, because I'm pretty sure your assignment 2 made you implement a problem using all three different types of flip-flops, which is a pain in the back. But just to reiterate, we have three main types of flip-flops. We have a D flip-flop, a T flip-flop, and a JK flip-flop. Before we get into that, I should go for latches first. If we look at latches, we can have a D latch and an SR latch. These are confusing. If you've ever watched a Minecraft Redstone video, you would know these names. Okay? A D latch is basically a box which takes in an input D, which stands for data, and it remembers that value, and it outputs it. We call Q the output, don't ask me why. So you give it a value D, and then you remove your value D, and it always outputs the Q. How does it know when to change? You have something called a control, or a clock, or an enable. So while the latch is enabled, it's actively remembering things. When this is 1, it's remembering things. When the control goes 0, it stops taking in anything else and just gives out the output. This is like you cramming before an exam. You have a period of time where you're receptive to information. You load all the information. After that, you can only output the information. You can't give out, you can't process anymore. So that's a latch. A D latch takes in the data and literally just copies out the data. An SR latch is a bit more basic in a sense. We have inputs S, R, I'm just going to put control here because I'm out of space. And then we have our output Q. Give me a second. Have our output Q. S stands for set, R stands for reset. While the latch is enabled and it's taking in more information, if set is true, then the output's going to be 1. You're setting the output value. If R is true, you're resetting the output value, so the output value is forced to 0. So using these two, using this one, it remembers what you give it. Using this, it's like a command. You're commanding it to either be 1, or you're commanding it to reset its value, and the control tells when it's receptive to more new changes. So very similar. You can actually have like a kind of adapter between D and SR latches, take in two inputs and you XOR them and you get the output. That's cool, but just to reiterate, latches are level sensitive, what we call. This is a keyword, level sensitive. When the control or clock or enable or whatever the hell you want to call it, when that is true, when its level is high, then it starts remembering things. If the level is low, then it just gives out the output. It no longer takes in new information. One thing you might note is that with an SR latch, if you set it, it goes to 1. If you reset it, it goes to 0. What if you set and reset at the same time? That's bad. It doesn't know what to do. This is called an undefined state or a race condition. You obviously cannot have set and reset at the same time, and that is the reason why we have D latches, because D latches never have an undefined state. The command you give it will always work, hopefully, if your circuit is good. Now, using latches, we've said that it passes through the value when the level is high. We can introduce the notion of flip-flops. So we have that, right? And if I have my input signal, I have my clock signal for a D flip-flop, or we'll call this D. Let's say I have some random wave here, right? The output of my D latch, the output of my D latch is going to be So right now the control is low, so it remembers the last value it had. Let's assume it's 0. While the control is high, it's actively taking in information. So we basically just kind of copy that, right? It's remembering things, and then at this point in time, when the control turns off, the value is low. So it remembers that value. And then when the control is high, it starts taking in information again. So this goes out like this. If the control turned low at this point in time, where the value is still high, it'll remember the high value until the control turns back on again. Right? It remembers the last value when the control was on. This works, but you'll notice that this is kind of unstable in a way, right? It's remembering things, but it keeps changing what it's remembered. So, the way we can do that is do something called edge triggering. You'll notice that the clock has an edge here, has another edge here. The point where the clock value changes, right? So we invent a new type of memory module that remembers the value at the instant of the clock edge. So this is called a flip-flop, and when it turns high, the value is that, so it remembers that value, flip-flop output. And then when it turns low, oh no. So you can have a positive edge or a negative edge, or you can have both edges. For argument's sake, let's make a positive edge triggered flip-flop, which means whenever the clock is a positive edge, then it remembers the value. So in that case, it encountered a positive edge here, the value was high, so it remembers that until the next positive edge. At this positive edge, the value was low, so it goes down low and it remembers that instead. Okay? This is a very common question that you will get in your exams. This is called a timing diagram. They'll give you an input signal, they'll give you a D latch or an SR latch or something, and they'll make you draw a nice timing diagram of what the output was. This is a good annotated diagram I have. This is your clock, and this is your data. This is your clock, it's a good old clock. This is your data. It changes, you'll notice, right before the clock edge, and this one changes right before the clock edge. So if we ignore the master one for now, just look at the output, it kind of normalizes the input, but aligns it to your clock edges. You'll notice that at this clock edge, this is a negative edge triggered flip-flop. At this negative edge, the data was 0, remember the 0, until the next negative edge. At this negative edge, the data was 1, so it goes up high. At this negative edge, data was 0, goes down low. Then at this negative edge, you'll notice that this little pulse does not happen when a negative edge is there. So this pulse gets flattened. It's not present when the flip-flop is sampling its data. So these ones get ignored, this one gets ignored, because at the negative edge it's 0 again. At this negative edge, it's high, so we start remembering that value. It's called a timing diagram. It's a very common question. Anyone have any questions about this? So this is a flip-flop. A flip-flop is edge triggered. We have 3 types of flip-flops, like you should be aware of. You have D flip-flop, a T flip-flop, and a JK flip-flop. We just looked at D. D stands for data. It remembers the data at a clock edge. All good? This is a JK flip-flop. That sounds funny. It's not joking. It's actually just a set-reset flip-flop. This is actually just your SR latch, or your set and reset, under a new name, because why the hell not? So J is your set here, and K is your reset here. It functions the exact same. Set and reset. There is nothing brand new about it. And then your T is what's actually new. T is your toggle. So if the toggle signal is high when the clock edge is sampled, then the output value will flip. This is a bit different to what we've taken in so far. But those are your 3 types of flip-flops. I think that's all you need to know for theory in terms of latches and flip-flops. So I think let's get cracking with the past paper questions. Otto can get a move on here.
Yeah.
Question 1.
can do that.
Question 1, I will upload these to the EdStem forum in a hot sec, but you can just watch. Oh, wait.
Okay. Let's do this. Okay, so let's begin with question 1. So this is question 1 of the 2024 paper. That was when we did it.
Yeah.
Huh. That's rather strange. Okay, so we're given a table of values. So a truth table right there. How do I get this? There's that straight. Okay. Simplify the function f using a k-map and express it as the minimal SOP. Okay? So there's a couple of main things to do here. We always know that Maxterms is always going to be a little bit goofy because you got to think about
it. For anyone online or anyone here, if you want the paper, I have uploaded the questions that we're doing onto the EdStem post that I have made a long while back and answered the crash course.
Sudarshan is the go. Okay, so let's begin. K-map. So as per usual, we don't want it in a table of values. We want a nice block of values. So let's begin with this. Typically, I like drawing them like so. As always, we have our grid. And then I don't know if they still do this, but A and B, C and D. You might like doing it the opposite way around, but we go ahead and we list out our values of A and B on this side and C and D on this side. So 0, 0, 0, 1, 1, 1, 1, 0. Okay, and we just fill in this table. Let's just fill in this table. So we look at A being 0 and B being 0. That will be the first 4 of these values. Okay, so I like doing this in groups of 4. So A and B are 0. I'm dealing with this column right over here. So I end up with 0, 1, 0, 1, 0. So I go 1, 0, go to the bottom, 1, 0. Okay? So first 2, bottom 2. First 2, bottom 2. This is how I'm going to go ahead and sequence this. Next, I look at the next 4, A0, B1. That is going to be the second column. And the sequence goes 0, 1, 1, 1. So I go 0, 1, 1, 1. Fantastic. I go ahead and I look at the next set of 4. It is 1, 0, so 1, 0, A to B. And then all of these are zeros, so I don't need to even care about the order. And then we have our final set, which are A and B active. 1, 0, 1, 0, 1, 0, 1, 0. Fantastic. So the little tricks I use there are just how we order things in gray code. Just remember, gray code is what we're using to order our columns and rows. Gray code is very cool because you just change one bit at a time and it actually makes the K-maps possible. Okay? Yeah. All right. Just a fun fact, if you used more bits in a K-map, you'd need to make it more dimensions, just because it wouldn't loop nicely. And so, let's get this going. So, now we need to find the minimal sum of products. So, what we can do here is identify all the groupings of things into little rectangles or squares. I look here, there is no squares. That is a shame. Some squares that might typically be hard to see would be using the 4 corners. Ooh, pencil, thank you. 4 corners, that is a square. If they have it running 2 and 2, that is also a square. Just remember, it can wrap around from any side, okay? Something to be mindful of. And so we can recognize our first one, just like this. I like using this one. Why? Because it is the only larger group that contains this top left square. I am less preferable to using this horizontal one on the bottom side. I look over here. I'm going to group these two. Likewise, I'm going to group this one, and now I have a choice. I have a choice of how I'm going to pick this last bit. Now, is there a best way? No. There are 3 ways I can do it, and it really doesn't matter all that much. So I'm going to pick this group. Now, something to note is, yes, you can repick the same values multiple times. It does not matter too much. It just helps us go ahead and restrict the number of terms in our min term, okay?
As long as each box you draw has at least one unique value is good.
Yes, having at least one unique value per box is very good. So if I went ahead and drew this little box over here, I would be very unhappy because those two are already in boxes and therefore not unique. Good stuff, thank you. Okay, so minimal, fantastic, sum of products. Let's go ahead and express this. So I say f, let's switch over back to the pen. F is going to be equal to, let's think of this. We got, a lot of these are columns. In fact, all of them are columns. I made that rather easy for myself. So I can begin with A and B both being complemented. And I'll just take, okay, look on the right-hand side. I need the top and bottom. What stays the same? This D bar stays the same, so D bar. I look over at my next column, which is going to be A bar B. So A bar B. And then I'm taking these three values. The first one, D stays the same. The second one, C stays the same. So I'm going to hit on D and then do the same thing for, oh, that's not going to be plus, it's going to be C. Same thing for C, okay? So C's are active, D's are active in the middle. Fantastic. Now we go ahead and we look at A, B. In this column, it's going to be top and bottom. So once again, this is going to be D bar. All right. Is there anything in A, B bar? No. And so that is what we get. This is going to be our minimal. There would be a variation in the solutions for this question just because this bottom bit at the bottom here could be one of three different groupings, okay? Could be one of three different groupings, all of the same size. If there was one that was like a bigger size than the others, we would probably pick that one to include this point, okay? Sound good? Let's keep it moving. So let's move on to part B, okay? So, total gate input cost of the implementation. I very much like just using the literals, terms, and complements kind of method. So let's think of this. I'm going to take 1, 2, 3, 1, 2, 3, 1, 2, 3, 12 literals. Now, mind you, the sum of products or product of sums may not typically be the most optimal gate input cost solution. It is just a very nice understanding-wise solution for us to put it in certain forms. In this instance, you can see how we could have grouped D and C as an addition through their common terms of A bar B. That's something if we were trying to optimize a system, potentially in that form. However, something to note is it would cause more layers of gates. Now, more layers of gates, typically, just from a design perspective, is going to increase propagation time, which you probably won't need to deal with in this course, quite frankly. It's just something to note, very much because I'm just going to doodle at the top of the page here. If I go ahead and I have many gates cascading to give me a low gate input cost because of whatever kind of thing I've done, it's still got to get through all those gates. And that's going to take time. That's going to take time that we may not want to put our system through. So instead, we might use twice as many gates just at the lowest level, then like a big OR function that's meant to be curled, where we just take the OR of all of these, and then that's still only two gate delays rather than using 3 or more gate delays. So that's just an interesting thing, just for everyone's enjoyment. So let's get back to the question. Let's not go on too great a tangent. We have total gate input cost, 12 literals, 4 terms. How many complements? We got 3 complements because this C is never complemented. Everything else at some point in time is complemented. So 3 complements equals a 19 gate input cost. Fantastic. All right. So that is very nice. Typically, it won't take you the longest. That's why it's 2 marks. Any questions for this section so far? All good. Worst case scenario, you go ahead and you draw out the thing, and you just calculate the number of inputs by the picture. Okay. They will typically try and make it a little difficult by having it be something rather convoluted to draw, but you got this. All right. Let's move forwards then. All right. So, part C. Derive an implementation of f in which d is applied at the input of a single 8-to-1 multiplexer in a minimal number of logic gates. Now, this is a very funny question. I did it a little bit beforehand to do a little bit of a preparation of this session, and we love multiplexers. Why? Because we can use them rather goofily. You'll also note that for this question, I very much used A and B. All right? What's the next most used term that I used? It would have been D. Now, why am I pointing these out? The reason I'm pointing this out is because in an 8-to-1 multiplexer, we know that we're going to use 3 selection channels. Selection channels let us very easily bypass the use of gates, okay? Because I can go ahead and, let's just draw up the big multiplexer. Recall, multiplexer has 1 output. This one is an 8-bit, so it's an 8-to-1, so it's going to use 3 selection channels. I'll call them S1, S2, S3. And then we're going to have 8 inputs. So let's hope I can divide this appropriately. Fantastic. So I'm just going to label it 000, 001, 010, 011. Did I do this right? Let's just continue. I think I need one more because I can't count. There we go. Okay, 100, 101, 110, and 111 finally. Okay, there is the mux. Now, sorry. Let's keep on moving. So, I've mentioned that A, B, and D have been very, very instrumental to the rest of the midterms in here, which is probably another reason forwards for why the midterms are so fantastic. So, what am I going to put on the selectors? That is a question. We're going to put A and B, certainly. So, let's put on A and B. What else are we going to put on there? Is there anything else useful? Well, there has to be. My next most used midterm is D, right? And so I'm going to chuck D on there. So by chucking my literals into the selections, I can really just go ahead and select each of these values in the truth table. Heck, if it was a 16-to-1 multiplexer, oh my gosh, that's just the table. That is just the table. Wow. Okay, so let's go ahead and actually fill this in. Now, you'll note that I've got A, B, and D here. If I'm working with not A, not B, not D, I'm going to call that 000. Now, what would I put here? Because I can't put like A, B, D in there. That wouldn't be very happy. I have to go ahead and say, oh, it's just always going to be 1. It's always going to be high because I've selected this channel, which is 000. So, without using any gates, I can just say 1. So this pulls it to high regardless, as long as I'm in that channel. Okay, does that hold for you guys? Is that all right? Okay, good stuff. I mean, if you wanted to convolute things and really give the marker a piece of your mind, you could plug in a not A in there. So if you're touching that channel, you know it's gonna be true. But please don't do that. They might punish you. So 001, let's go ahead and look at this. So AB, D bar was good. How about A, B, D? Is there any, sorry, A bar, B bar, D? There is no such A bar, B bar, D. So we would put a 0 in here. Next up, we're looking at A bar, B, and then D bar. So A bar, B, and then D bar, A bar, B. So let's just identify the 2 terms that satisfy our first 2 selectors, which are A bar, B. That's these 2. Now, we need to look at, does it have D bar? We know that this one has D, so it's certainly not going to be the case. How about this one with C? The point is, we need to now make this contingent on C. So, we need to plug in a C over here. This is purely for the fact that C is not in our selectors, and so we have a term that depends on the value of C. All right. Moving forwards, a bar BD is very much just this term right here, so you can say that's a 1. Then we have a B bar. There are no such terms with a B bar. That would be in this fourth column. And so a B bar will always be 0. A B bar, still 0. And then we hit AB. AB is only active for D bar. So if we have D, which is going to be given by the last one will be 0, the second last will be 1. All right. And then over here would be F as our output. How do we feel about that kind of multiplexer? Fantastic. All right. And I believe, well, let's double check the number of logic gates. How many logic gates did I use, guys? 0. Oh my gosh. Thank you very much. So that is question 1. Good stuff.
I will note one caveat. Otto's method is really good if they ask you to design your own one. He unfortunately would not get all 6 marks for this question because the question asked in which D is applied at the input. He did not apply D at the input.
Oh no.
So this is good if they did not specify this section. This is how you would get the minimal amount of gates and inputs in like variance. However, because their constraint is D is applied at the input, he would not get good marks for this question.
Exactly. So I have quite frankly made up a question. We do not want to do that. We want to look at where D is applied to the input. Okay. Now, mind you, the input, it's not talking about the selectors. Now, that is something to note. They can be a little finicky with the language. So let's go ahead and try and redo this question a little bit.
I'll redo it in a different way.
You will?
In a different way.
Let's do this.
So another way of doing this is very similar to what he's done with the minterms. However, you can derive it straight from the truth table. If you take, so here where our constraint is that D is applied at the input. So D is applied at the input. A, B, and C are our select lines. So like Otto has said, when we head over here, A, B, D, we look at the minterms here, they're applied at the select. So we can actually group this in terms of A, B, C at the select. You'll notice that if A, B, C select is 0, 0, 0, then it's these 2 rows. It's no other rows. So like that, if we group every pair of select terms, like that, you'll notice that this is when 0, 0, 0, this is 0, 0, 1, this is 0, 1, 0, etc., etc., etc. So you'll notice that what is varying is the D term. So we essentially want to express F as a function of D. So you'll note here that F here is the inverse of D. 0, 1 becomes 1, 0. So this is D naught. Here, same thing. Here, F is just exactly what D is. So that's just D. Here, F is always 1 regardless of what D is. So you can just say 1. Just like that here, F is always 0, F is always 0, F is the inverse, and F is the inverse again. Therefore, if we draw up our, that's not a multiplexer. If we draw up our good old multiplexer with one output, 1, 2, 3, 4, 5, 6, 7, 8 inputs, A, B, C, then just rattling off if the order is 0, 1, 2, 3, 4, 5, 6, 7, then our inputs should be D bar, D bar, D, 1, 0, 0, D bar, D bar. Fast way of doing it. Make sense? Question?
It says minimal number of logic gates. They don't actually care about, like, because it's just D and it's constant, then we don't have to really worry about it.
Correct.
Cool.
I think they just mean don't unnecessarily add in like an extra, I don't know, OR gate. Like, F here is technically OR of D, right? Like, that's stupid. That's I think that's all they're saying. Cool. Does that make sense? Let's move on. Question 2. 2009 paper. This is possibly my favorite question I've ever seen. It is... I love the reactions. Yes, it looks very painful. Yes, it probably is painful. But it very well sums up the entire finite state machine process. It's on EdStem, bro. It's on Net Forum. You can get it from there. It sums up the entire process, and it's basically what you would have done in your assignment, but in one question, right? So it asks us, just like in reading time, you have a big fat state diagram that looks like death. Using the state diagram, write up a state table. Get an output sequence. Minimize the number of states, derive a reduced state table, and using an implication table, and then convert the reduced Mealy machine to a Moore machine using a state table, and then implement it using flip-flops. Okay, this is a stupidly long question, but let's see if we can speedrun it. Excuse me. The following Mealy state machine with one input x and one output z is defined by the state diagram. Okay? This is a Mealy machine because the outputs are dependent on the inputs. Yes? The other option is a Moore machine in which the transitions are obviously your inputs and the state has an output associated with it. Familiar with the two different types? A Mealy machine has the ones out here, and a Moore machine has more information inside the circle. Cool? Okay. Write the state table for the Mealy machine. I did not think this through, and it's on the opposite page. I'm going to draw one up right now. Excuse me, you can also draw one up while we wait. What do we need? Present, next, and out. X is 0, x1, draw that. And then we have A, B, C, D, E, F, G, H. We also need a present state. Present, so we have A, B, C, D, E, F, G, H. Let's just make it pretty while we're here. There we go. This is our state table. Did I copy everything I need? Yes. Awesome. The way we do this is we kind of just read off the state diagram here, right? So at our present state, A, if x equals 0, then it goes to B. Yes? So if x equals 0, it goes to B. If x equals 1, it goes to C. If x equals 0, the output is 1. If x equals 1, the output is also 1. Make sense? Well, we just rattle this off for every single state in the state diagram. So just rapid fire. B in 0 and 1 has an output of 0 and 0, goes to E and G. So it's E, G, 0, 0. C, this is an interesting one. When the input is 0, it's a self loop. Okay, the output is 1, and it stays back in C. So the input is 0, next state is C, input is 1, next state is A, and this goes 1, 0. D goes D, B, 0, 1. A, B, C, D, E goes F, C, 1, 1. 1, 1. From F, we go to H, D, 0, 0. 0, 0. From G, we go back to G, or F with 0 and 1. G, F, 0, 1. And H, we go to F, C, 1, 1. F, C, 1, 1. Did everyone get this far? Check out. Okay. E, G, C, A, D, B, F, C, H, D, G, F, F, C. 0, 0, 1, 0, 0, 1, 1, 1. 0, 0, 0, 1, 1, 1. Awesome. I don't think I made a mistake there. Great start. This is our state transition table for the Mealy. Oh, sorry. Could you see it earlier? Yeah, okay. This is our state transition table for the Mealy machine. We'll come back to this question later. We'll just get cracking. Our next question is minimize the number of states and derive the reduced state transition table. So I'm just going to have to quickly copy it back here. A, B, C, D, E, F, G, H. Next time, do not print on double-sided paper. E, G, C, A, D, B, F, C, H, D, G, F, F, C. 1100100111000111. Awesome. The way this table works is we want to see if any of these states are actually equivalent to each other. Many of these states, well, some of these states will actually just be the exact same state with the exact same outputs, but just it's another dot on the diagram for no good reason whatsoever. The way we can find this is by checking if both, well, first of all, for two states to be equivalent, their outputs should be equivalent, right? If your output's two different things and they're not the same state. So A and B cannot be equivalent because their outputs are immediately different. However, if you look at A and E, they have the same outputs. So A and E could be the same state if the next states are equivalent. A's next state is B and C. E goes to F and C. So immediately, C is already the same. So A and E are equivalent states if B and F are equivalent states. You could keep following this through. You look at B and F and you're like, oh, they could be equivalent. But there's more to keep going. That's a pain in the back. You will go into like some deep rabbit hole and you will never recover. The way we fix this is called an implication table. It's just a very standardized way to figure this out. So we draw our states here, A, B, C, D, E, F, G. You'll notice that H is missing. This is because if I was to have a H here, and I was to have, again, A, B, C, that's D, E, F, G, H, having a H and a H on the same thing is useless because they are the same already. So what we instead do is we remove this extra one and we kind of downshift all our values. So we have B, C, D, E, F, G, and H. That way, every single pairing of values is still the same. Because if it goes one way, it obviously goes the other way as well. If A and B are equivalent, B and A are also equivalent by logicness. So now we'd go through, we'd see, okay, we're looking for A. Is A equivalent to B? It cannot be. It can never be because the outputs are different. So you can put a nice big fat X in there. We look at C. Well, we can just see which ones the outputs match. Outputs match for E and H. So E and H are tentative, and then we can put X's through the other ones. A is equivalent to E if C equals C and B equals D. Sorry, B equals F. C and C are obviously equivalent. So our condition here is that B must be equivalent to F. So I'll put BF in here. And then A is equivalent to H if, oh, it's the same condition again. So I can put a good old BF here because again, C is already equivalent. Then we can look at B. The only other one with the 0, 0 is F, so we can immediately rule out all the other ones. And then with F, for B and F to be equivalent, E and H should be the same, as well as G and D. So we can put E and, what's it? This is BF, EH, GD. EH, GD. Is that legible? I hope so. C, 1, 0. Nothing else has an output of 1, 0. So C is not equivalent to anything else. D is a 0, 1. Only other 0, 1 is G. So we look at D and G. This is a very interesting one, which we'll get to in a hot sec. DG and BF. So what this says is that D and G are equivalent if D and G are equivalent. This is a very circular dependency. And what this means is that it is true. If D and G are equivalent, then they are equivalent. So we can immediately say that this has been fulfilled. This condition is fulfilled already. So our only real condition is BF. You can see that so many different things rely on BF being true. So we'll get there. And then nothing else, I believe, interacts with D, 0, 1. Yeah, nothing else is 0, 1. So these are all ruled out. And then E is a 1, 1. So it's E is equivalent to A if B and F. Oh, E doesn't have an A anymore. E between F, G, and H. E and H are equivalent. There we go. It's another kind of equivalency. E and H are equivalent if F and F are equivalent, and they are. And C are equivalent. Therefore, E and H are the exact same state. Hell yeah, that's the reaction. So we can just put a tick in there immediately. The other ones are dead. So you'll notice E and H have become equivalent, which means this one has become equivalent. As in, this condition has been fulfilled. So now, BF are true if G and D are equivalent. And G and D are true if BF are equivalent. This is another circular dependency. Therefore, they are equivalent. So we can just kind of tick those off, put a nice little tick in here, and we can start going, well, B and F are the same. So those are the same as well. And then we'll finish off the last ones. I got too hasty there, sorry. F does not equal G and H, and G does not equal H. Okay, I wasn't hasty. And we can see that we've really minimized a quite fair few states. So we've said that A and D are the same state, A and H are the same state, B and F are the same state, and D and G are the same state, right? This means we only have 4 states remaining. We've just said, so, and derive the reduced state transition table. So wherever we have, which ones can we do? Wherever we have an E, we can just replace that with an A, right? So we cross this out, and this becomes an A. And then an F and a B are the same. So wherever we have an F here, make it a B. We have no Fs, so we delete that one. And then that's an F. G is equivalent to D. Wherever we see a G here, make that a D. So make that a D, and then you can kill G. And the last one, H is equivalent to A. So we delete that, and there's no H's here. So this is our reduced state transition table. It's that, ignore the E and G, it's now A and D, CCA, DDB, and the outputs are 11001001. Okay? And now the next question is where the fun comes in. Convert this to an equivalent Moore machine. Like we said, in a Moore machine, the outputs are dependent on the present state, not the input. Give me a sec. Yeah. So the way we do this conversion can get a bit tricky. So in a Moore machine, we said that the output is tied to the next state. Yes? So the way we have to look through here is see that A, when the input is 0, the next state is B, and the output is 1. What other states have a next state of B, and is their output 1? If so, then we can immediately just push that output to the state. Does that make a bit of sense? If all the states where their next state is B, if they all have an output of 1, then we can just push the output of 1 to the B state. If 2 states had different outputs going to B, then we have a problem. We need to make a new intermediate state. However, in this case, we look at whichever states have a next state of B. These 2. When the next state is B, the output is 1. And here, when the next state is B, the output is 1. So we're good. So we can immediately just put a B. In a B state, the output is 1. With an A, when there's an A, the next state is B when the input is 0. Okay? Now we look at C. The next state goes to C, and the output is 1. This one also has a next state of C. The output's also 1. So that's good. So we can pop down our C, and we can pop down a 1. Because whenever we go to a C, the output is always 1. Likewise, whichever ones have a next state of D. This one goes to a D and the output is 0. Nothing else has a next state of D. Oh wait, this one does. This one has a next state of D, output is 0. Next state of D, output is 0. Therefore, we can set that. And then with A, these two have a next state of A, and the output's again 0. Right? AA, 0, 0. Therefore, we can tie that in. And what we've done, this question has been very nice to us, and the next states have just perfectly tied in for a Mealy machine. Many times, if, for example, this was a 1 here, then these two have a mismatch, right? The next state is A, but the output is different. So we'd have to make a kind of fake A state, or a Z state in this example. Oh, we can't use Z. Make it an E state. We'll have to make a new state. So instead of C going to A, we'll have to get a C going to a brand new state E, and then their next states are the same. But the output is different, if the output was different. Cool? I think I said too many words there. Wes?
Is there a reason why we can't use logic gates to say what the output is dependent on the state? Or is that no longer a Moore machine because you're now...
Yeah.
It's
Yeah.
no longer a Moore
Yeah.
machine if you do that?
Yeah.
Oh.
So our state machine, if we had an AND gate here, like if I had an AND gate here, that's a bit weird, all right? You can't do that. But to reiterate, because I think I spoke too much. Okay. Our next states, we are comfortable that, let's say C. C and C, the output is always 1 and 1. Therefore, we can say that the C state has an output of 1. The output is always 1 when you're going to the C state. So we can plot this here. If, for example, this one actually had an output of 0, then C and C have an output of 1 and 0. These are different. We can't have two outputs for a single state. So what we need to do is make a brand new state. Let me call this P. I'm calling it P. Therefore, nothing else has a C. So now we can tie C has an output of 1, and we can say P has an output of 0. So we've had to make a brand new state to account for the difference in outputs. Make sense? And now when we were drawing this, what we would do is we would say P0, but P and C have the same next states. So this would be same as CA. And back here, we can just copy down, because we've said here, if we've made that modification, this would be BP, AD, CA, DB, and this would be PCA0. So you'll notice that C and P have the same next states because we just copied C to make P. However, they have different outputs of 1 and 0. Oh, sorry. Please do comment if I go off the screen, because I'm looking down, I can't see that. Okay? So P and C have the same next states, but their outputs are different, so we've made a new state. Going back to our original question, this did not exist. A had a next state of, what was the original one? C, I believe, yeah. C, and then this was just a C, and that was a 1. So this is our final output, okay? ABC 0, bad 1, CCA 1, DDB 0. Cool? And to draw this as a Moore machine, we would have A has an output of 0, would have B has an output of 1, C has an output of 1, D has an output of 0, and then A goes to B and A goes to C if it's a 0 and a 1. B goes to A and D with a 0 and a 1. C goes to itself and A with a 0 and a 1. And then D goes to itself and B with a 0 and a 1. Cool? Awesome. So what we've just done was we've taken this terrifying looking abomination of a Mealy machine. We have gone through drawing a state table. We have minimized the number of states using an implication table. Using, there we go, this can be done using 4 states. We've got our 4 final states. Then we've converted that to a more machine because happily all the outputs worked out, and then we've drawn this more machine. So this state diagram is equivalent to this state diagram. Cool? Awesome. Now we get to the spicy bit. This more machine is to be implemented using D flip-flops and other additional logic. I will need a brand new page here.
It's so mean though, like they make you make the mealy thing, and then if you get the mealy thing wrong, then your next question is also going to be wrong because...
Carry on error.
Oh, they're okay.
There's always carry on error.
Oh, okay.
There's-
Never mind, let's chill then.
Yeah. Yeah, it's human marked. Unlike your Moodle quizzes, which are auto marked using backslashes for some bizarre reason, this opinion does not reflect the course, it's my own opinion. These ones are human marked. So there is lots of leniency for carry on error. It's very clear that you've actually, like if I did get this wrong, it's clear that you've actually tried. You will get most of the marks. You'll lose like 1 mark tops. Okay. Implementation time.
Just with this,
Uh-huh.
notice we skipped question B, which is
Yes.
input.
Yes.
Would you only do that after we simplify it, or?
Yeah, so it makes life easier once you simplify it. Yeah, that's why I said we'll wait, because the outputs become really easy using a more machine. All right? So using a mealy machine, you have to be like, well, when does the input change? There's an order you have to read. And it just died. All right, we'll wait for it to come back. Is it overheating? It's blinking. Please live. Okay. Implement this using D flip-flops and additional logic. Has the zoom level changed, Otto? Has the zoom level changed? Yeah. And focus. Perfect. The more machine is to be implemented. So let me copy down my... Actually, before I copy it down, we've all done this in the assignment, right? So the way we do this is using a D flip-flop. We want to find out... Well, firstly, we would... Here we go. Choose and list binary code assignments for the states. So we need to give each state a binary value. So we can give A a value of 0, 0. We can give this a value of 0, 0, 0, 1, 1, 0, and 1, 1. Just basically. And then we would go and substitute all of our next states for our binary numbers that we've given it. And then outputs, 0 and 1. And we'll need some kind of logic to determine the next state based on our input. So that means that our D input to the flip-flop of t plus 1 is a function of the first digit of the state, second digit of the state. Let's call this D0, D1, and the input. Make sense? So we're going to have to make a K-map where the next data input is some form of combination of XORs and ANDs and ORs and NOTs with the current states and the input. So let's do this. Let's give this our present state. Let's say this is our D1, D0. We have our states of 0, 0. I'm going to double it. You'll see why in a hot second. 0, 1, 0, 0. I said double and I stopped doubling. Muscle memory. 0, 1, 1, 0, 0, 1, 1, 1, 1. So this represents A, this is B, this is C, this is D. All right? And then we want a line for our inputs. So now the reason I've doubled it is so that I can kind of break out the inputs into their own rows. Over here, we have two different columns for the inputs, and it's hard to make a truth table. So what I've done is I've kind of collapsed that into X And now we can just say 0, 1, 0, 1, 0, 1, 0, 1. Does that make sense? So I've gone from x being on this axis to x being on this axis, so we can now calculate the next state as a function of these three. Like we said, the next state should be a function of these three. And then next state of d1 of t plus 1 and d0 of t plus 1. So with an input of 0, A goes to B. B is 0, 1. With an input of 1, A goes to C. C is 1, 0. Make sense? So now we just follow this procedure all the way down. I'm going to try and do it quickly. Hopefully I don't make any mistakes. 0, 0. B 0, 1, 1 goes to D, which is 1, 1. C goes to C, which is 1, 0. C goes to A, which is 0, 1. D goes to D, which is 1, 1. And then D goes to B, which is 1, 0. Cool. This is our present. This is our next. And finally, we want our output Z. Right?
Sorry. What binary numbers are you using for each state?
Arbitrary. I just decided to give it 0, 0, 0, 1, 1, 0, 1, 1. I've decided to assign, like the question here, part E, says choose, just choose, and list the assignments for the states. So I have arbitrarily chosen A to be 0, 0, B to be 0, 1, C to be 1, 0, and D to be 1, 1. You could do this in any random order. The reason I chose this is because it kind of muscle memory makes it easy just to go in very good order. Like I could make A be 1, 1, and the next one be 0, 0. But that's weird, and I would hate you if I was marking that. Anyways,
I just don't see any next state being 0, 0, so I'm in the middle I'm just blind. Never mind. Don't worry about it.
next state, there should be two next states of 0, 0, right? Yep, so that's B0 should be 0, 0, and then C1 should be 0, 0. You're right, there's a mistake here. Thank you. 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0. Ooh, this one might be wrong. D goes to B. There we go, B0, 1. This is a mistake. There we go, it's very easy to make mistakes here. This is 0, 1. Cool. And then our output Z, we'll note that because this was drawn as a Moore machine, the output is dependent on the present state. So the output here will be equivalent, right? Because it's still, present state is still A. So now we can just copy that. This is 1, 1, this is 1, 1, this is 0, 0. Does that make sense? Just for like viewing pleasure. I can't draw straight lines, but there you go. This kind of segregates the current states. Oh, the stream has been broken for a long time. My bad. I'll fix that. There we go. Stream's back. Sincere apologies. Video frozen. How long ago was that? Hopefully not too much. You can hear my audio. That should be enough. It was when the camera went down. Yeah, it's back now. Okay. Online viewers, apologies. I've just gone through and written out a brand new state table. There we go. So this now tells us what our next D value should be based on the present state, and what our output should be based on the present states. So now we can regard this as a standard 3-variable truth table. This is our function output. We draw a K-map, and we rinse and repeat for our 3 different functions, right? So let's speed run. 1, 2, 3, 4, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, line through. Let's make this D1, D0, and X. And then, so let's call this our K-map for D1 of T plus 1. This has 0, 1, 0, 1, 1, 0, 1, 0. So this would go 0, 1, 0, 1, 1, 0, 1, 0. Right? And using our K-map methods, we have one nice rectangle here, and we have a nice rectangle that kind of falls out of the edge here. Right? And this would be what changes here. X does not change, and X is a 0. So this would be X bar D1 plus X D1 bar X. You'll notice this is an XOR. This is basically just X XORed with D1, right? Therefore, D1 of T plus 1 equals X XORed with D plus 1. Rinse and repeat. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. D1, D0, X. Let's call this table a function for D0 of T plus 1. Still working online, right? Awesome. 1, 0, 0, 1, 0, 0, 1, 1. 1, 0, 0, 1, 0, 0, 1, 1. Awesome. This is going to be a lonely little sad question.
Do you know if we're allowed to use XOR in the exam? Because on only assignment they wouldn't let us.
Should be fine. Should be fine. If the question says use standard gates, then maybe not, then don't. But if not specified otherwise, XORs are a valid gate to use. If it asks you to get the gate input cost, then XORs are not valid.
That makes sense.
Make sense?
Yeah.
Cool. D0 of T plus 1. This is a lonely box here. We can draw a nice one here and a nice one here. This would become X D0 plus D1 D0 plus, this is all of them, complement, X D1 D0 complement. So this is our function for D0. And our very final one, I'm going to cram it in here. I apologize. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. D1, D0, X. Output here, 0, 0, 1, 1, 1, 1, 0, 0. 0, 0, 1, 1, 1, 1, 0, 0. That's very nice. Question? Off the page. Thank you. Back one. Okay, and we can draw a nice one here, nice one here. Just by practice, this is an XOR between D1 and D0. Therefore, this is Z equals D1 XORed with D0. Okay? We can kind of visualize that here. And now we have our three equations for D1, D0, and Z. Now, this was our flip-flop and output equation. So this has been done, this has been done. And now draw the logic diagram that implements the machine. If I shift over here, this is where it gets messy. I'm gonna go, oh no, it's annoying. Okay. So let's draw our little flip-flop here. This is going to be D1. This is going to be data. Then we can draw D0. And then we only have two flip-flops for the states, and the output is a function of these. D. And then we'll have our input coming in from somewhere off the edge. Thank you very much. Okay, so we have said that D1 is the XOR of X and the current D1. The next D1 is the XOR. I was way too close. Apologies. Is the XOR of the current D1 and the X. Okay? D0 was a massively convoluted function, which I guess I have to draw. Bring that back here. We're going to AND X and D0. We're going to OR that with D1 and D0. D1, D0. When you were drawing this, you'd probably use a ruler and make it a bit neater. You would, this X inside is still allowed, but if you want to just make it neater and you have any crossing lines, you would do the little, that, across a line. That I missed badly. You would have a line, if you want to cross that line, you'd put a little thing to show that it's not intersecting. You have that, and then our final Z output is D1 XOR D0, so that's quite pretty. This is Z. So, and then you'd have a clock, this is clock. I also missed a gate here. This would be the AND of, I've messed it up badly here. Yeah, white out. There we go. Have an AND gate here. This output, I'm going to make a nice fat OR gate. And then our final AND gate of X0, D1 and D0, 0. So this would be and that goes into an AND gate. Right, and another NOT gate, another NOT gate. Please, I would recommend using pencils so you don't make the same mistakes I do and you have all this white out. But anyways, this would be that, this would jump and go there, and then this would just be X. Okay? This is our implementation of this. And with that, we have almost finished this entire question. So just to reiterate, what we've done is we've taken a big fat state machine, mealy diagram, drawn a state table, flipped over, minimized the number of states, drawn that, and then converted that to a Moore machine, drawn the Moore machine diagram. Then we went here, we drew a nice table of what the present states, the next states, and then we can find out what values these need to be. Then we found out all the functions required to implement those, and then finally we drew this abomination. Just as a little side note, if they asked you to implement this using a T flip-flop, for example, right? You would have to check whether you need to toggle that value or not. So you would not toggle D1, but here you would have to toggle D0, okay? And then you would not toggle, you would toggle this, and you wouldn't toggle this, etc. So you would have an extra 2 columns here of T1 and T0. And then finally, it asked us to write the output sequence with an input sequence of X equals 0, 1, 0, 0, 0, 1, 0, 1. And we, initial state of A, from A. So if we go here, do the bend, from A. Our output at A is 0. And then we give it a 1, we move to C, our output is 1. Then we give it a 0, we stay at C. Our output is 0. We give it a 0, we stay. From C, question?
Output is 1 at C.
Oh, I'm stupid, thank you. 1, 1, 1. But we're staying at C and we're just giving it more zeros with an output of 1, you're right. And then over here, when we give it a 1, we finally leave that infinite loop and we go to A. Our output at A is 0. And then we give it a 0, we go to B. The output is 1. We give it a 1, we go to D, the output is 0. The end. You could do this using a Mealy diagram. You should get the same answer, but there is the order in which you should calculate it, which is provide the input, read the output, and then proceed to the next state. Okay? Otherwise, you will get the output of the wrong state. Which is why I said we can leave this one to the very end, because this just makes it way easier to read than having to jiggle with these. And that is this question Done. Very last question we have today. I'm sure this is everyone's worst nightmare after submitting the assignment, is some Verilog on paper. If they are evil, they can ask you to write Verilog by hand. This has happened in past exams. They make you write Verilog by hand. Oopsies, question?
Would you have to use like perfect syntax?
Oh, no,
So if
enough
you-
syntax.
No.
No, it doesn't. They're not going to like actually compile it, but as long as it kind of vaguely makes sense, that's fine. But in this question, brand new page, we are given this whole dump of code. Right? All this code. Part A, is this a mealy or more machine? Part B, what type of modeling is described here? Is it data flow, structural, or behavioral? And part C is draw a state table or diagram. Excuse me. Okay. How do we proceed to analyze this? Anyone want to take a stab? Or would you just like me to do it? Question? Yeah.
Well, the output at that SSC at the top is the register Z.
Mm-hmm.